Sharon Peacock is an academic clinical microbiologist at the London School of Hygiene and Tropical Medicine and the Wellcome Trust Sanger Institute. Prior to this, she was professor of clinical microbiology at the University of Cambridge and head of bacterial diseases research at the Mahadon Oxford Tropical Medicine Research Unit at Mahadon University in Bangkok, Thailand. Her current research focus is on the role of pathogen sequencing and genomics in diagnostic and public health microbiology, antimicrobial resistance, and pathogen biology. Her particular interests are in the implementation of sequencing technologies into routine clinical practice so as to inform and improve infection control practice and prevent nosocomial infections, and in the characterization of genetic relatedness and transmission of pathogenic bacteria in different reservoirs, including humans, livestock, the food chain, and sewage. Sharon is a fellow of the Academy of Medical Sciences in Britain and the American Academy of Microbiology. She's an elected member of EMBO and was awarded a Commander of the British Empire, or was named a Commander of the British Empire for services to medical microbiology in 2015. Please welcome to the stage Sharon Peacock to present her lecture, A Topsy-Turvy World Where Pathogen Sequencing Leads Infection Control Practice. I got it almost.
Thank you so much. Thank you. Thank you so much for that very kind introduction. And before I start, I'd like to thank the organisers so much for giving me the opportunity to speak with you today. It really is a great honour to speak at this opening session. So in the next 25 minutes, what I aim to do is to talk about how we can dramatically improve the way we detect outbreaks in hospitals through a fundamental redesign in our methodology, in which pathogen sequencing takes the leads and directs activities. So on to my declarations. I'm employed at the London School of Hygiene and Tropical Medicine by the Wellcome Trust and at Cambridge University Hospitals. My research funding is from the Wellcome Trust and the UK Department of Health. I have industrial collaborations with Illumina and NextGen Diagnostics, and I have consultancies with Specific and NextGen Diagnostics. So I'd like to start talking about hospital outbreak detection and describing it as an unseen but essential service that occurs across all of healthcare provision. I like to compare it with a smoke detector. It's there looking for outbreaks, and then as soon as one is detected, we pounce into action and nip it in the bud. Now, outbreak detection is a major plank of our safety culture. It improves the quality of our patient care, it saves lives from nosocomial infection, and also, nosocomial infection may affect reimbursement and lead to fines. And also, detecting outbreaks is as important as it ever was. This is because the risk of outbreaks are increasing. For example, we're doing more to patients, and more patients are requiring intensive care. We have an aging patient population. Now, if you put those two together, older people, people in intensive care, they're at high risk of nosocomial pathogens and nosocomial infections. Now, where I come from in the UK, our National Health Service is having problems with overcrowded hospitals and ageing hospital estates. Now, they're both associated with difficulty in doing effective infection control. The other point to make is that harm from outbreaks is going up because of antimicrobial resistance. Now, you'll see here a map from CDC of carbapenem-resistant Enterobacteriaceae associated with nosocomial infection. And so these pathogens are spreading around the US and elsewhere. Now, the WHO have estimated that the risk of dying if you have a drug-resistant infection is around twice that if you have a drug-susceptible infection. Now, outbreak detection is incredibly important. And going back to the smoke detector analogy, smoke detectors are very sensitive. They detect a whiff of smoke and then set off a course of action. Now, what I'd like to ask you is, do we do that with outbreaks? What is our time to detection? And are we as quick about pouncing into action? Now, in order to think about that, I want to take you back 150 years or more to where outbreak investigation really started. And this was in London with John Snow. Now, he's one of the founders of modern epidemiology, and he's particularly famous for his outbreak investigation in 1854 of a cholera outbreak. Now, this is the map he drew of cholera cases, and what he did was he plotted on the map, and then he interviewed people to find out where they had their household water source from. By doing this, he focused his attention on a water pump in Broad Street, and the evidence was so compelling, he convinced the council to take the handle off the pump, and the outbreak came to a close. Now, if we think about this and compare that to what we do now, 150 years later, what I would propose to you is that what we do actually hasn't changed that much. We have surveillance, epidemiological investigation, and intervention. If we break that down into the component parts, surveillance means we have a daily list of patients with indicator organisms that might be MRSA, or it might be multi-drug resistant gram-negatives. Now, we look for 2 patients that are positive for the same indicator organism, and if we find them, we then look for an overlap in time and place. If we see that, we investigate by ward visits and initial assessment, and we may go on to investigate through an infection control investigation before we take action to contain further spread. Now, we might also use 2 things: antibiotic resistance pattern, which is where we look at the pattern of resistance in the offending organisms to see if they match, and that's a surrogate of relatedness, i.e. they may be involved in an outbreak. The other thing we may do is bacterial typing, but there's a problem with both of those adjunctive methods. First of all, although antibiotic-resistant patterns are really easy to get hold of, the lab generates them anyway, and that they are not a good surrogate for bacterial relatedness. The reason for this is they lack sensitivity, so highly related isolates of the same species can have a different pattern. They lack specificity, so unrelated isolates of the same species can share the same pattern. Now, looking at what we do for typing, there's a whole range of methods we've got available, but unfortunately they all lack fine-scale discrimination. Now, that's problematic because nosocomial pathogens are often in very defined small number of clones, and we need to be able to tell one isolate from another within a clone and not between clones. So this brings me round to proposing a new redesign for hospital outbreak detection. It starts with routine sequencing of the nosocomial pathogens of your choice, be they MRSA or multi-drug resistant gram-negatives. You sequence them as they're cultured in the laboratory. Now, based on the sequence data, you look at the probability of the outbreak based on the degree of genetic relatedness. You haven't looked at epidemiology at this point, and you cluster that into high possible or low probability of an outbreak. You then take action only on those patients that have got organisms in the high category. Now, when you look at that, it's a one-day process and a one-step to action, i.e. sequencing. Now, if we compare that with what we do currently, it's favourable because that has multiple steps to action. So what I'm suggesting is this proposed redesign would mean that we'd be acting more like a smoke detector and pouncing into action. Now, the next 3 slides are going to start to build the evidence base for suggesting that we should use sequencing in infection control epidemiology. Now, the first is some work published in the New England Journal of Medicine in 2012, and it was the first application of rapid sequencing of a hospital outbreak in our neonatal intensive care unit back in Cambridge. Now, we used a benchtop sequencer, and we could sequence over a 24-hour run period, which was revolutionary at the time, actually. And we sequenced 7 MRSA from patients linked to a known outbreak, and 4 MRSA from patients not linked to the outbreak. Now, please note that all 11 isolates were indistinguishable by standard typing. Now, we compared the genomes, and this is a phylogenetic tree based on mutations in what's called the core genome, i.e. all the genes that are conserved in that bacterial species. And you'll see here that the cluster, if I can move no, I'm not going to be able to do that. In the blue circle, you can see the isolates that are associated with the cluster, which are really clearly distinguished from those that were not associated with the cluster. So many other people have shown as well that sequencing is better than current typing for outbreaks. My slides are not progressing. Could I have the next slide, please, whilst you're sorting it out? Thank you. So the next stage was what we wanted to do was compare conventional infection control detection of outbreaks with sequence-informed outbreak investigation. And we got a marvellous opportunity in our hospital in a special care baby unit, or SCBU, in Cambridge. Now, we had 3 infants who were MRSA positive, and the infection control team had picked this up themselves. And they considered that this was a potential outbreak. So it triggered a major investigation and a 6-month look back for other cases. Next slide, please. Okay. Great, thank you. Thank you. Hopefully my mouse works now. If not, perhaps somebody could look at it whilst I'm speaking. Okay, so I'm sorry about that. So we had 3 MRSA positive infants on our special care baby unit. We did a major look back, and what you'll see here is the timeline. So along the x-axis, you've got days from 0 to 350. Each row is an infant, and the size of the block is the length that the patient was in hospital. Now, the infection control did a really detailed investigation. They concluded there was not enough evidence for an outbreak. Next slide, please. Can I have the next slide, please? Thank you. So what we did was we sequenced those 14 isolates and compared their genomes, and you'll see the phylogenetic tree there. There were only 20 SNPs different in the 14 isolates. So that was really clear evidence for an outbreak. Next slide, please. So strong evidence for an extended outbreak. So why is it that we found an outbreak with sequencing, but infection control thought not? Next slide, please. What you'll see here is a circle around the first 3 cases. The antibiotic resistance pattern was actually variable across the patients, and that confused the infection control team. In addition, the red stars show that there were gaps when no MRSA carriers were in the special care baby unit at all. And that is partly why they concluded there wasn't an outbreak. Next slide. Now I want to show you another example where we've used sequencing to improve infection control epidemiology. This time it's 4 patients with healthcare-associated MRSA bacteremia. They were on the same ward at overlapping times. You can see the timeline, P1, 2, 3, and 4. Those are the patients. They were in hospital over a fairly extended period of time. And they were on the same ward with overlapping times. So the black bars are when they were in the hepatology ward in Cambridge. So we know they had overlapping admission times. The antibiotic susceptibility pattern was identical for isolates from 3 cases. And they all had the same type by sequence typing. So the infection control officers said the outbreak is highly likely. And I think that's quite reasonable. Next slide. So what we did was we sequenced the MRSA from those 4 cases, which you'll see in red, purple, blue, and green. We also sequenced MRSA from carriers on the same ward in the last 12 months in grey. And so the phylogenetic tree that you'll see there shows that those MRSA cases are completely separated. So there's absolutely no doubt in our minds that there was no outbreak going on there. So in the first instance, we ruled in an outbreak, and in the second, we ruled it out. Next slide. So having shown you that sequencing is superior to standard outbreak detection, the question is when to use it. We have option 1, where we could simply replace sequencing for bacterial typing. Could you progress the slide, please? So you could replace, no, not that fast. Thank you. Could you, yep. No. Oh, okay, I'll do that when I want the slide to go, okay? So can we go back? Right, let's stick with that. Apologies. So we have option 1, which is replacing our bacterial typing with sequencing, so it comes in really late. We've got option 2, which is this new redesign that I'm proposing. Now, when we look at the evidence, we like redesign option 2. And what I'm going to do now is show you the evidence that supports that. So, this is going back to our SCBU outbreak. And the first thing I would say is somewhat observational. What I would have dearly liked to have done is actually detected those first 3 cases that occurred by sequencing so that we prevented all of those other patients getting MRSA positive. Just as well, we've all got a sense of humour, isn't it? Another point to make is that, and this is a critical point, is that blind sequencing detects cryptic transmission. That means transmission that infection control didn't know about. And this is a beautiful example of that. So we sequenced additional MRSA isolates cultured by the routine lab around the time of the SCBU outbreak, and we didn't have any epidemiological information at this point. What we found was that 10 isolates that were blindly sequenced were related to the outbreak MRSA. So look at the phylogenetic tree. You'll see those 10 cases in the icons. There's icons for babies and adult men and women, and they're all highly related. So who were these people? What you'll see on the timeline plotted there is there are 2 clusters, and then the other cases expand across the time piece, including for about 6 months after the end of the SCBU outbreak. So what we then did was we went to the patient notes and looked to see how we could actually link those new cryptic cases in with the current outbreak. So this figure shows it all. And it's a beautiful example of genetic forensic epidemiology. So you'll see here that there are cases that have been in the community, never been in hospital, cases that had been in the maternity ward and in SCBU but were not known to be MRSA positive. But now if you start to look at the cases that link to each other, you can actually see, for example, the baby in green in the second column links to their mother. So there's a transmission pattern there. So the mother transmitted MRSA to another mother on the maternity ward. That mother then transmitted MRSA to their partner. So this shows you that MRSA is spreading within and between family clusters. Now I'd like to pause for a moment and show you the consequences of the SCBU outbreak and what might have been prevented with those first 3 cases being detected. Now, this organism had a high attack rate, and 10 patients had deep soft tissue abscess, 5 affecting the breast, 4 patients had superficial pustules, and then on the right you can see all of the healthcare requirements that these patients had in breast surgery clinic, GP practice visits, emergency department. 2 people were admitted to hospital for breast surgery, and there were 26 MRSA decolonization treatments. So there's already compelling evidence that if we can detect outbreaks much earlier, we can prevent that sort of morbidity. But probably the best evidence we've had so far for sequence first is this work published in Science Translational Medicine last year. Now what we did was we based ourselves in our large diagnostic micro lab serving 3 hospitals and 75 GP surgeries, and we simply identified everyone who had a sample that year that was MRSA positive, and that's nearly 1,500 people. For those people, we worked out where and when the sample had come from, where they lived, whether they were in hospital, and if so, where they'd been to. Then we sequenced at least 1 isolate from every case, actually 2 in most cases. Then we had the sequence data and the epi data, and we brought them together. Now, what we found, to our surprise, was 173 outbreaks in amongst those patients. That's around 40% of everybody could be linked to an outbreak, around 600 people. Now, if you look at the 40% of outbreaks and say, did they happen in hospital or in the community, around 2/3 occurred only in the hospitals. About 1/6 only occurred in communities, including GP surgeries, and about 1/6 had people from both. So this methodology starts to allow you to see how people move from the hospital and community back again, transmitting their nosocomial pathogens. Now, an amazing thing about this study is that no outbreaks were previously recognized, and the biggest had 44 patients in it. So you might be saying, why on earth are there so many missing cases of transmission? And I think this image really says it all. So in A, we have a really simple timeline of 8 patients who have been in ward green. The second one up is the index case. And so for an infection control officer looking at that timeline, it's really obvious. They're all linked in the same time and place. Now look at the figure on the right, B. Now this is a timeline for 7 patients. They're all involved in an outbreak, but the blocks of colours shows the wards they've been going through in our hospital. And it's really complicated. So how can an infection control officer make sense of that in a very easy and straightforward way? But sequencing gets to the nub of the problem immediately. So now this is my important slide, particularly important. I want to talk about how we're implementing Sequence First in Cambridge in a routine diagnostic lab. And most of the work goes on in day 1. So what we have is we have a red flag for target organisms. We're starting with the MRSA, moving on to gram-negatives. So we have a Keystra system, and MRSA is set up as a red flag system, and plates are put to one side by our colleagues in the lab. We then, by lunchtime, we go and get those plates, and what we're looking for is the primary culture plate. We want to get to that sample as soon as possible, and it doesn't matter if it's got other bacteria on there. So what we do is we do a colony pick, and we extract from that. So that gets us to DNA sequencing as soon as possible, and we do a sequencing library prep, so that can all be automated, and then we go and sequence, which is run overnight. So this whole process takes a day. We put the sequencer on overnight to have the results by the morning. Now, I'm not going to endorse any particular sequencing technology, but we've examined what to use, and we're using an Illumina mini-seq for 2 reasons, really. One is it's got a 13-hour runtime, which suits our overnight cycle. And the other is that we can sequence 21 isolates at the same time with 3 controls. So for us, that works. For your own labs, you'd have to consider what's on the market and what suits you best. Now, the morning of day 2, we have our sequence files, and they're automatically uploaded into a cloud-based analysis pipeline. Now, this pipeline has been built on the back of Wellcome Sanger Institute analysis pipelines in collaboration with NextGen Diagnostics and ourselves. And what this does is it automatically compares all your test genomes with the database that you have from the last 3 to 6 months, or however long you've been doing this for. The beauty of this is that you don't need any informatic expertise, and it is all done in a matter of 45 minutes or less. So it actually takes away the issue of needing to be an expert in reading sequence data. Then the data is actually drawn into a hospital IT network and merged with patient and laboratory data. We have Epic, which I know many of you will be using. So the data is brought together to generate a report. Now, this is all done behind a firewall, so there's no issues of confidentiality. And a report is generated for infection control. Now, our first generation of report is quite simple, and it's based on some really excellent work done by Jennifer Gardy on a report for tuberculosis. And you'll see here that there's patient details and so on. There's a summary that says something like, this isolate is methicillin-resistant Staphylococcus aureus. It belongs to a cluster suggesting transmission. And then there's a box at the bottom that shows your test isolate compared with other isolates and says whether it's likely to be involved in an outbreak or not. Now, I've said previously we have these 3 categories, and we've based that on cutoff of genomic similarity modelled on our 12-month MRSA data that I mentioned previously. And the calculation is based on expected mutation rate in that particular pathogen over time, times by the genetic diversity of that pathogen within a host at any given time, because there's always some diversity in the organism that an individual is carrying. So finally, I'd like to come on to the issue of cost effectiveness, which we all need to understand in order to implement new technologies. So we worked with York Health Economic Consortium to develop a decision tree model to estimate the impact of Sequence First using our 12-month MRSA cohort. So here we compared current standard with Sequence First, and in the current standard we've made an assumption that you have an outbreak of cases 1 and 2, who then can transmit their organism onto other cases 3, 4, and 5, and some proportion of those patients are going to develop MRSA infection. Now, in Sequence First, our idea is that, like a very sensitive smoke detector, we spot cases 1 and 2 and then nip it in the bud. We do not get transmission to other cases, and we prevent MRSA infection occurring in those patients. Now, based on that, we found that there was a $22 upside for every patient admitted to the hospital, which for 60,000 patients admitted per year adds up to $1.5 million of savings every year for a single hospital. And then if we factor in the cost of sequencing, the ratio of sequencing versus the cost of savings is a ratio of about 1 to 3. Now, we're beginning to gather data from a prospective evaluation of this, but this is a strong indication of financial saving. So I'd like to finish my talk with a critically important slide and to acknowledge all of the marvelous people that have helped to get us to where we are now. People in my group, in particular for this work, Francesca Coll, who analysed the MRSA one-year cohort, Beth Blaine and Kathy Raven, who are doing much of the laboratory work to translate sequencing in our laboratory. I'd like to thank Nick Brown, David Enoch, and Estee Torok, who've been utterly generous in allowing us to use clinical specimens and get access to the laboratory in Cambridge. In the Sanger Institute, I'd like to thank Simon Harris, Gordon Dugan, and particularly Julian Parkhill, who's been a terrific partner over the last 10 years. I'd like to thank York Health Economic Consortium and also colleagues at NextGen Diagnostics, Paul Rhodes and Eugene Brigham. So finally, I haven't got any question time here, but I would be really delighted if you could come to my fireside chat tomorrow at 11 o'clock. And I'm very much looking forward to getting into a dialogue with you about whether you're interested in being an early adopter of this technology. So thank you so much for listening. Thank you.